Now, let's do this in the context of a problem. And so let me just make up a problem. Let's say we had find the volume, or no, I'm sorry, not find the volume. Find the triple integral of E, and then let's put something in here like x squared plus y squared plus z dv, where E is a solid that's bounded by and then I'm going to put, I'm just make something up, the paraboloid z is equal to, and then I'm going to put an upside down paraboloid. I'll say 4 minus x squared minus y squared, and the plane z is equal to 0. So what I want to do is I want to try to figure out what that is and then see if I can make up boundaries for it. And we had something similar to this, and I said we were going to do that problem today. And so I'm going to go back and redo that problem. But first, let's talk about how this thing's going to look like. If you can remember how paraboloids act, pretend that this is just y is equal to 4 minus x squared, and look at that as a parabola, and imagine how that would look like. What does y is equal to 4 minus x squared parabola look like? Should be up by 4 and go opening downward. Yeah, because of the minus sign over here. So it's opening downward and it's moved up a few units. So that would be how the parabola looks like. Now if we're translating that to a paraboloid, then my guess would be that this is a paraboloid upside down 4 units up. Boy, this is a crappy looking paraboloid. All right, so this is the paraboloid, and so the E volume that we're looking at is in here, that whole volume. And we could try to figure out what the Z values are. It looks like the Z value, if I were to draw a line parallel to the Z axis, I would hit this solid when Z is equal to 0 and get out of that solid when Z is equal to the paraboloid. Now dealing with X and Y, I'll put Y first and then X. It'll be a little slightly more challenging, and this is the shadow that this is making on the XY plane. So if I were to look at that shadow, I would be looking at a circle. I wonder what the radius is. How do we find the radius of this circle? Make z equals 0 for the paraboloid. It's the paraboloid. The circle is when the paraboloid is intersecting the xy plane. So basically when these two graphs intersect. So if we make z equal to 0 here, and then rewrite it so that it looks like an equation of a circle, you get x squared plus y squared is equal to 2 squared. And that's going to be the radius of your circle, which means after I figured out my third dimension variable, my innermost integral in my triple integral, the two outermost integral is looking at a circle. Now I decided, for some reason here, I decided to integrate with respect to y first, so if I were to draw a line parallel to the y-axis, I would go in and out of a couple of functions that are basically the circle y is a function of. So if I solve for y here, I'm going to get plus and minus the square root of 4 minus x squared. And that's going to be my two functions. The one below is the one I enter in, and the one above is the one I get out of. And then my x limits are what? Negative 2 to 2. I could go from 0 to 2. I could take advantage of symmetry, but if you're dealing with a function here, the symmetry has to apply to that function also. And I see an x squared plus y squared here, so that is symmetric around the origin, but the z out here is making it probably not so symmetric, so I want to be a little careful about using symmetry here. All right, so these are my limits, and I can write my integral. Let me see. The middle one is going to be a lot. So my integrand is x squared plus y squared plus z. And I'm going to integrate with respect to z first. Looks like that's what we decided. I decided 4 minus x squared minus y squared. Then I'm going to integrate with respect to y next. So that's going to go from negative square root of 4 minus x squared to positive 4 minus x squared. And then I'll integrate with respect to x, finally, from negative 2 to 2. But the thing is that if we integrate with respect to z first, and then we do this work, and we integrate with respect to x and y after that, we basically can think about just turning that into polar coordinates so that we have a nicer integral to deal with, right? So the question is, why wait that long? Why can't we just change it to polar coordinates now? Well, it turns out that cylindrical coordinates is polar coordinates in 3D. So cylindrical coordinates equals polar coordinates in 3D. So it's really just a transformation where x is going to be the x value for polar coordinates, y is the y value for polar coordinates, and z, turns out that we're not going to do anything with z. We'll just leave it as z. Okay? So let's take a look at the polar coordinate equations. And we'll come back to redoing this whole problem again in polar coordinates, or in cylindrical coordinates. All right, so cylindrical coordinates is a transformation that takes your x, y, z into r and theta and z. So x is going to be r cosine theta, y is going to be r sine theta, and z is just going to be z. Now we'll have an issue, of course, when we do the transformation from dv to our dr, d theta, and dz. But we can think about filling this blank in by thinking about the Jacobian, since we already introduced the Jacobian. We talked about the Jacobian in 2 dimensions, but really there's a Jacobian in 3 dimensions that follow the same kind of rules. So remember that we're going from a seemingly complicated solid in XYZ, and then there's a transformation R theta Z that hopefully would be a lot easier to deal with. And so we're going from, they call it a pullback because the transformation goes from R theta Z. These are like the independent variables, R theta and Z, and your dependent variables are like X, Y, and Z. So those are like your outputs. So that's why in this particular scenario they kind of think about it as a pullback. So the Jacobian, if you remember, is going to be the partial of the dependent variables. This time there's 3 of them. And then the partial, this is just a notation, R, theta, and Z. And then we just want the positive determinant of, now we have 3 going in and 3 coming out, so this should be a 3 by 3 matrix. So we're going to take the partial of x with respect to r, partial of x with respect to theta, partial of x with respect to z, partial of y with respect to r, partial of y with respect to theta, partial of y with respect to z, partial of z with respect to r, partial of z with respect to theta, partial of z with respect to z. I probably should have called z a different variable because it would just be a dummy variable anyways. But since z is equal to z, then it really doesn't matter. We can call it the same thing. So if you look at this and take derivatives, and if you look back at our notes for the Jacobian that we found for polar coordinates, we'll see that it's almost exactly the same. Partial of x with respect to r is just cosine theta, and partial of x with respect to theta is negative r sine theta. Now the partial of x with respect to z, I don't see any z's here, so this is constant with respect to z, so I think this is just going to be 0. And if I fill in the rest of this, we'll see that this upper corner over here is just like the polar coordinate Jacobian that we computed last week. And you got 0s, 0s, and 1s. And so if I were to take the determinant of this without doing any work, let me just tell you that this is just going to equal to r. Just like the polar coordinates was equal to r. And you can do the computation if you want and think about expanding along the 3rd row for those matrix people. But that's your differential that comes out. That's your change of variable differential compensation. Okay? So whenever you use cylindrical coordinates, this is what we need to do. We need to include that extra r. Just like when we use polar coordinates, we need to include the extra r. So tomorrow you'll see another transformation that's going to be a little bit more complicated than this. It's not as simple as just bringing a 2-dimensional idea to 3 dimensions, but it's going to look at a holistic transformation in 3D, from 3D to 3D. So this is really just our transformation from 2D to 2D, polar coordinates, except we're extending it to the z making a cylinder, so to speak, on the z. So when we bring this up to cylindrical coordinates, we're going to use almost the same kind of polar coordinate rules. Okay, so far? All right, now let's take a look at our problem and see how we can bring this to polar coordinates. So let's see. I think I want pieces of this. Let's take the original problem. Let's take this graph, crappy looking graph. Now let's have this information. All right, I think I got everything I need. I don't need to rewrite that complicated looking limit setup that we had. Do we want this? Let's take a picture of this also. All right, 1, 2, 3, whoops. 1, 2, 3, 4. So let's take a look at the equation and the description of E. We have the drawing all set up over here, and we have the two-dimensional picture over here. And let's say now that we're going to go into cylindrical coordinates. So cylindrical coordinates have a z, an r, and a theta. And if I basically write down what I had for z from before, because z is equal to z, right? I can just simply copy what I had before. Except I have a little bit of a problem here, because if I say that I'm going to integrate with respect to z and then eventually integrate with respect to r and theta, I have x's and y's involved in my z. So I can't. I don't think I can deal with that. What do I need to do? What? Yeah. So what I have here is simply an equation. If I were to convert this into polar coordinates with the polar coordinate transformation, by the way, I wrote down r is equal to cosine, or x is equal to r cosine theta, and y is equal to r sine theta, but then I should have put this here, but I thought maybe it was kind of obvious. X squared plus y squared is equal to r squared. It's the same transformation that we had in polar, right, independent of the z. So I can use that same transformation over here. And I have a minus x squared minus y squared. That's just equal to negative r squared. So I have my z is actually equal to 4 minus r squared. And that's what I'll do here. I'll replace that with 4 minus r squared. And now my z limits are a function of r and theta, although I don't see theta there, but it's a function of r and theta technically. Okay? So once that's figured out, I'm now left to figuring out this two-dimensional graph in terms of r and theta, which should be fairly straightforward. My r goes from a radial distance of 0 from the origin to a radial distance of 2, and my theta goes all the way around to 2 pi. So I have a much simpler looking set of limits, and it gets even nicer when I put it into this integral, because x squared plus y squared will just become an r squared. So I will have my triple integral looking like, in cylindrical coordinates, looking like my z is going to go from 0 to 4 minus r squared. Oops, I usually put down my integrand first. X squared plus y squared is r squared. z is just equal to z, so I'll just leave it as a z. And then my dv, remember, produces that extra r from the Jacobian. And then I'm deciding to integrate with respect to z first. And then I'm going to integrate with respect to r from 0 to 2. And then with respect to theta from 0 to 2 pi. A quick look at this. I have my two inner integrals that are not a function of theta, so I can take that out of the integral of theta just to make things slightly easier, but then I don't think I can take the inner integral out. So I won't do the integral, but just to get you a step into an easy computation, I can have the integral from 0 to 2 pi with respect to theta as an integral that's not dependent on the other two integrals. But the other two integrals here, they look like they're dependent on each other, so I would keep it the same and work it out from inside out. So these would be my limits. Yeah? I think if it's something like this, this is easy enough to be able to integrate. I think if I was going to give you an integral, it wouldn't be more difficult than this to actually integrate. But I think for most of the tests, I'll just be setting up the integral. But I think there was one where I actually had you integrate it, so, or my last time. All right, so is this okay? All right, now the power of this cylindrical coordinate business isn't just to change back into polar, but if you remember the problem that we had the other day, or yesterday, we went sideways. We integrated with respect to x first or something like that. And so because of the idea of a transformation, when you transform the cylindrical coordinates, we don't have to just restrict ourselves to having x is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. We could shuffle those things around, and I'll show you what I mean by that after we pull out the actual problem that we were working on. Are the notes up? Yep, notes are up. So let's take a look at our problem from oh, it's all annotated on. Gonna look a little messy. So let's take a look at this and quickly redraw. So this is a parabola going sideways, going from zero to 5. This is 5. We have a circle here. The parabola goes back there. And then, so it basically stops here. And then our x, y, z looks like that. So our shadow is on the yz plane. And because our shadow is a circle on the yz plane, it's going to make me want to think that we should be using our cylindrical coordinates. But our cylindrical coordinates, if you remember, it says x is equal to something, y is equal to something, and z is equal to something else. So I want to kind of change that around a little bit. It's still going to be in cylindrical coordinates, but let's take a look at it from a different point of view now. Since x acts like a z, how a z would normally act like, I would probably leave this x as x, kind of like how we had z is equal to z in cylindrical coordinates. Now, I'm looking at this, and when you get to this step, it doesn't really matter which one is going to be your r cosine and r sine theta. But if you want to kind of follow with the convention of how this is going to be drawn, since I'm looking at the y and the y is acting like the x-axis, I probably want to call that r cosine theta. But again, it still doesn't matter. So if I shuffle those functions around to a different variable, we don't necessarily have to restrict ourselves to saying x is always going to have to always be r cosine theta, or y is going to always have to be r sine theta. It doesn't have to be always like that. So in this case, we can shuffle things around and make it look like this. So when we see a y squared plus z squared around anywhere, we can think about that as r squared based on these two things. And still our dv is still going to be equal to r dr d theta dz. Okay? And when you shuffle things around in linear algebra, sometimes your determinant might come out to be negative, but you know, the Jacobian is always looking for the positive values of things anyway, so we don't have to worry about negative stuff. Okay? All right, so if you remember, our x went from, we go parallel to the x-axis, we enter through the paraboloid, and we get out through the plane, x is equal to 5. So our x here is going to go from 0 to the the paraboloid first. The paraboloid, 5 y squared plus 5z squared less than x and less than 5. Yeah. Oh, this one? Yeah. Thank you. What? Squared. All right, so our x is equal to this, and our y and z would become r and theta. Based on this picture here. I think the radius of this circle is 1, right? When we did it the other time. So r is just going to go from 0 to 1. Oh, I need to fix one more thing. What do I need to fix? What? The y squared plus z squared, the x limits, the lower limits here. I lost all the y's and z's, and so that just has to become r squared. So if you factor out a 5, you get y squared plus z squared, which is equal to r squared. So I'll change that. Is there enough? Oh, instead of r dr d theta dx, yeah, that's the other one. Because we changed instead of a z, so this is an x. So usually the order, when I write this down, the order really doesn't matter, but most likely it's the dx or the dz that's going to come first, and then dr d theta comes last. All right, so we have these limits all figured out, and then we can just set up our integral. then we can do a little comparison and see how our integral looked like from before. So this is an important part over here. This is just the x. And so x is equal to x from our transformation. So this integrand is just going to be 10x, like it was before. If you had a y or a z, then we would have to do these other replacements over here. But here it's just 10x. And then our d's x first. Our x goes from 5 to 5r squared. And then our r and theta goes from 0 to 1 and 0 to 2 pi. I'm missing something. R.
Would the lower limit be 5r squared?
Yeah, boy, I'm just not on it, huh?
Are you getting sick? Do you have to move the final?
Oh, always like this. The other days I'm just lucky. Is it right? I hope.
I don't know. I wouldn't trust me.
Yeah, I wouldn't trust me either.
And if you're going to say I wouldn't trust you. I say, whoa.
Yeah. I wouldn't want to take my test.
Nope. No, thank you.
But see, I don't have to. You guys have to. So.
No, but you should, for like moral support.
Sometimes I do.
Martin Luther King would. Did you get good grades in
I don't remember Calc 3. It's kind of like a blur. It was already the third quarter in Santa Cruz, and so I was in the partying mode already. The first couple of semesters, I was kind of serious and stuff, and after that, well, you know, I mean, I still got an A in the class. I just don't remember too much of it. I just remember my teacher. He was a weirdo. He's like, you know, you talk about asymptotes. You know, he said you'd go to some asymptotic trip to infinity and then come back from the other side. And he would talk like a stoner. And
So you got that from him a little bit?
so I think, well,
Maybe your memory stayed in fourth dimension.
yeah, maybe
That's
I
why
was.
you did so well in the class.
I was always in the fourth dimension in that class. I don't know. I don't remember. But I never got 100% in any of my classes. I got like a couple of 99s out of 100 in my exams and stuff like that. 97 on a final. And I never got 100. It always kind of bothered me. Little details. All right. Back to this business. So the idea is that we're looking at something in 3 dimensions. We're bringing it down to 2 dimensions, and we're seeing circles. We're seeing polar remnants of polar coordinate stuff. And so we can bring everything in from the 3rd dimension, everything into a 3D polar called cylindrical coordinate system. And so this is essentially what we have. You should look at the book, because I think the book has a nice drawing of how the dr, d theta, and dz look like. And they look like a piece of a cylinder, which is why they call it cylindrical coordinates. And they talk about how to come up with this r. We came up with it using the Jacobian, because I've already talked about it. But in the book, they hadn't talked about the Jacobian yet. And so that idea isn't for them to show you. So they show you how to get this r in a different way. And you should look through that, because I think it's kind of interesting. All right, let's take a look and see what kind of problems might come up in the homework set. If we take a look at some sample problems from the book. This is 7 or 8? 7? No, it's 8. Too late. What's going to pop up for me? Oh, 8. I just want to get to the integrals. So we did a problem, I think, where we had a sphere and then we drilled a hole in it. Do you remember doing that problem? Oh, maybe this is a good time to tell you what I was going to tell you earlier. So let me tell you something about the triple integrals and the volumes, and then we can take a look at double integrals and areas. So far, when we think about double integrals, we think about double integrals as the volume of stuff, right? So let's think about a double integral and what that means. So when you compute this double integral over some d or r, I think d, of some function x, y, dA, geometrically this gives the volume under f over the region D, right? So that's what it does. Now let's think about a special type of function f to put in here. What if f of xy was equal to 1? Now picture this. You have a region D on the xy plane. And then what's f of x is equal to 1? What is that? Z is equal to 1, which is a plane parallel to the xy plane. Z is equal to 1. And then what we're essentially finding, let me see if I can draw this. What we're essentially finding is a volume of this solid that's right above this of height 1. Do you see that? You know what that is? So the volume here, let's say the volume is equal to, I don't know, K. Put a number there if you want, 15 or 7.5 or whatever. So let's say the volume is equal to K. What else do you know is equal to K? You understand what I'm asking? What else is equal to K in this picture? Yeah, yeah. But geometrically, what else is equal to K in this picture? What? Area times height. Think about that. Area times height. The volume, area times height, the volume is equal to area times height. What's the height of this? 1. What else is equal to K? The area. Area is equal to K. Now the only difference is, if you were in physics, your units would just be different. But the numerical value of the volume that we just found is equal to, numerically equal to the area. So this double integral, if you put 1 in there, is really just looking for that area. So let's see if that was convincing. Based on what we just said, we can rewrite our double integral over d. If you have a 1 in there, dA, this is equal to the area of d. Right? So does that idea make sense? So we're used to thinking about a double integral as a volume, and technically it is, because it's a function over here in terms of a unit of measurement. So that's one dimension of unit of measurement, and then the dA has a dx and dy, so that's two other measures of units of measurement that we're going to multiply together. So this is something cubic measurement of something. So this is a three-dimensional volume. But if you put 1 in here, numerically, we are looking at the same numerical value for the area. Does that make sense? Because if we apply that to 3 dimensions, what does that mean? That means now in 3D, if the integrand was equal to 1, then this is equal to the volume of E, numerically, a three-dimensional volume. So again, the units are different. This would be cubic inches, and if we were to put a different function here, our calculation for the integral would be inches to the 4th power, whatever that means. But numerically, we're still getting the volume. Okay? Now, let's take a problem from double integral, maybe not the applications, but when we're first talking about double integrals. And we could do polar coordinates or let's take a look at this problem and see what we did to get this problem. Can you guys still see that? All right, so this is how we did it last time. But now, pretend that we didn't know how to do it last time, and now we're dealing with triple integrals and we're asked to find the volume of something. So we're looking for the volume. So if I want to use triple integrals to find volumes, automatically I think about, oh, okay, this is going to be a triple integral of the solid of 1 dV. So now I just have to figure out what the solid looks like. Okay? The solid apparently looks like this. And so if I'm going to set up my triple integral for the solid, I will find my z and then my x and my y. Okay? Now I'm looking at that solid, and I will draw a line parallel to the z-axis and see where I'm going to enter the region and exit the region. And it looks like based on my drawing over here, or based on these graphs over here, I can say that if I'm going to integrate with respect to z, I'm going to go into z is equal to 0, and z is equal to 6x squared plus 4y squared. And then my x, if I look at this, this is kind of set up for me already, so I'm just going to copy that down. My x would go from 0 to y, and my z would go from, or my y would go from 0 to 3. I'm just going to steal that information from our notes from last time. But now what I have set up is a triple integral. And so what's my triple integral look like? My triple integral looks like this. It's the integral of 1, right? And I'm integrating with respect to z first, so I'm going to say 1 dz, integrate z from 0 to 6x squared plus 4y squared. And then I'll integrate with respect to x. X goes from 0 to y, and then I'll integrate with respect to y from 0 to 3. Okay? So now I've just used a triple integral to find the volume. So how is this related to our double integral? What? It's volume. Double integral is the volume. Triple should be a 4-dimensional volume. But what's happening? Okay, well, this is my innermost integral. Why don't I take that off to the side here? And integrate it. So I'll integrate this. Integral of 1 with respect to z is what? I have a z. I want to evaluate that from 0 to this thing. And if I do that, I'm just going to get 6x squared plus 4y squared, right? So I'll put that into this integral, and then I still have 2 integrals wrapped around it. So in here goes 6x squared plus 4y squared. And outside I have my dx still. Dx goes from 0 to y, and my dy, that goes from 0 to 3. Now, look. Exactly the same thing, right? So numerically, we're getting the same value for the volume using double integrals and the volume using triple integrals if we have the integrand to be equal to 1. Okay? So there's something interesting going on there. And we can even take this down one more level to our single integrals. So let's summarize this in my previous page over here. So it looks like a triple integral of E 1 dV is going to equal to the volume of E. The double integral of D 1 dA is equal to the area of D. Now, I'm going to write this a couple of different ways, but the next one I want to write down is the integral from A to B of 1 dx. What's this equal to? X evaluated from A to B, which is equal to what? B minus A. So what if I rewrite that? Integral of an interval from A to B, for example, of 1 dx. What's B minus A in terms of that interval? The distance, or the length. How do you spell length? G-H-T-H? G-H-T or G-T-A?
I think it's silent W. It's so bad.
Right. As in right? So the single, double, and triple integral is kind of like if we have the function that we're putting into those double or single or triple integrals is equal to 1, which it is in these cases, we're putting 1 in for the function, then we're saying that next dimension up that it would be looking for is really, it's really just have a numerical value of 1. So when we think of base times height, and the height is 1, then we're really just measuring the base. That's what's happening here. If we have area times the height, and the height is 1, then we're really just finding area. So that's the same thing with the volume. If we have a volume times 1, normally we would think about that as a hypervolume, something in the 4th dimension. But since it's since the 4th dimension only contributes a factor of 1, you're just multiplying it by 1, which numerically is still going to be the volume of the original 3-dimensional shape. So that's what we have there. So we're finding volumes. So we can find volumes using triple integrals. Okay? We're going to keep talking about this later on because sometimes knowing that our integrand is equal to 1 will be important for us, and then it's just a matter of doing geometry instead of having to, try to figure out some complicated formula for some integral that we may or may not know. All right. Now, I kind of went off track because when I was looking at one of the problems, it's asking us to use triple integrals to find volumes of something. So now let's do number 14 or 15. You guys want to do one of these? Let's do number 14. So here they're asking us to use cylindrical coordinates to find the volume that lies within the cylinder and the sphere. So let's go back to cylindrical coordinates. We have a sphere, radius 7. We have a cylinder, radius 4. And then we want the volume that lies between both of them. So it's on the inside here that we want. Okay. So since we are looking for volume and looking at, the sphere and how perfectly symmetric it is, we can just go from 0 to the top half of the sphere instead of going from the bottom half of the sphere to the top half of the sphere. So we can just go from 0 to the top half of the sphere. And after we do that, we are looking at your two-dimensional region, which is a radius 4 circle. X squared plus y squared is equal to 4 squared, 16. So that's basically our setup, it looks like. So if we're going to use triple integrals, our volume setup is going to be, I'm going to set up the triple integral first because I want to put down the 1 there. And then let's talk about the limits. So in cylindrical coordinates, it looks like my z is going to remain my z, and then my r and theta is going to be with the x and the y. So my z limits if I'm going to multiply this by 2 and just take half of it, I could imagine my z going into my region, my solid, when z is equal to what? No. Z. So my solid is this. Let me see if I can redraw my solid. I'm cutting it off right here. So my solid starts from here. It goes up to the top half of the sphere. So this is my solid. I had a bottom half over here that I'm ignoring because I'm just going to multiply it by 2. So what's my lower limit for my z? 0. So I'm on the xy plane. So this is going to be 0. My lower limit's going to be 0. And then I'll be inside of my three-dimensional region solid until I get out of what? What am I getting out of here? The sphere in terms of z. So I want to get z by itself here. So z is equal to, and then I'm looking at the top half, so it's a positive square root of 49 minus x squared minus y squared. And of course, if I want to change that into polar coordinates, I need to do the x squared plus y squared business, right? So let me just do that here. In polar coordinates, this is square root of 49 minus r squared. So those are my limits for my z. And remember that this got switched from Cartesian to polar, so I need to throw in that extra r. All right? So after that, we're basically done because now we just have to put r and theta in. And r and theta, because this is a perfect circle, it's just going to be constants. 0 to 4, 0 to 2 pi. So I'm integrating with respect to r from 0 to 4. And then I'm integrating with respect to theta from 0 to 2 pi. Okay, so now I've used, I could have used polar coordinates in 2 dimensions or with a double integral, but we can also use triple integrals. Make sure your integrand is 1, then you're getting the same numerical value for the volume. Okay? All right, so I think those are all the types of questions that we would be looking at. Here they have more applications in cylindrical coordinates, like finding the center of mass business. You guys can figure that out. All right, so we've gone through polar coordinates and double integrals, cylindrical coordinates and triple integrals. We're going to go through one more coordinate system, and then that would complete our double and triple integral study before we get into some other weird integrals after the test. All right? So keep up with your homework so that you're kind of retaining these things. Yeah? Tuesday. Yeah. Yeah, the study guide is almost done, so I'll post that up probably by tomorrow. Anything else? Yeah, you get 1 sheet of notes for the test.
Back and forth?
Yep, back and front.